Since last century, 20th century, it became apparent that we had laws of motion, we had mechanics, right? Things in motion, and how those laws explain how things behave when they are moving. But it became apparent that those relationships were not enough to explain the behavior of atoms or behavior of electrons. And hence, many people started investigating what experiments can we do to understand the behavior of electrons. And that became what you call as a special kind of area called quantum mechanics. So you'll see that quantum mechanics is, uh, it's mostly mathematical, but if you understand the basic concepts of how electrons or how particles are moving, it helps us a great lot. Now, when you say quantum mechanics, we have to understand many basic concepts before we get into what you call quantum numbers. A set of four numbers which defines every particle and how it would behave. Now, when you say that atoms and electrons, they don't obey the laws of physics, so for the bigger things that we know, like things in motion, we have to describe the behavior where now when we are talking about small things, we don't have gravity, we don't have large forces acting on that. So there is a different set of forces that we are interested in. Mostly those forces are electrostatic forces, forces that are, uh, they have their origin in electronics. They have their origin in charge. Sorry, electronics is of course the bigger thing, but charge. So the forces that we'll be dealing with, most of them will be related to how charge travels. And when you say charge, the basic definition of charge is electron, right? And then holes, but we'll stick to electron for now. So how would one electron feel the force from another atom, which has its own electrons? How would an electron feel the forces from nucleus, which have positive charge in it? So it's all about forces. We call them when something it is feeling a force, it has potential to move, right? So we talk about potential energy. When something is moving, what kind of energy does it have?
Kinetic.
Kinetic.
Kinetic energy. So at the end of the day, we will be looking at kinetic energy and potential energy. Now, when something is moving, depending on its mass and velocity, what kind of quantity do we measure for two things which may have different mass?
Momentum.
Momentum, right? So we measure momentum for things that have certain mass and certain velocity. These are all the mechanics, or these are all the things that we use to define bigger things, especially when they're moving or if they have energy. But now when we talk about small things, the same measurements, the same quantities, but measured differently because now the rules are changed. So that's what quantum mechanics does for us. The rules of quantum mechanics are different than classical or large scale mechanics. So hence we have to uh, use some things which we may not see in everyday life, but my goal here is that to explore it with you so we all will be able to see how they would be, where they come from, those quantities that we use to understand the quantum mechanics or their energy at that small scale. So I was talking about that last century. So they started developing quantum theory because they were interested in, especially at that time, that how does the light and matter interact? And they were doing lots of experiments which showed that light has a wave character. We take it for granted, right? So we say light travels as waves. But there were lots of experiments which showed that light also has kind of a particle behavior. We'll look at some of those examples. So, but the first experiment that I would like to talk about today is that how do we relate the atomic theory, quantum mechanics, and electron models? And how do we use the uh, experimental knowledge to understand the energy of an electron, for example? So a very classical experiment, it's called photoelectric effect. Now, what is photoelectric effect? The idea was that if you have a heated sample and called a black body radiation, and if you measure the radiation from a black body uh, uh, sample, you measure that there are discrete units of energy that you get. Okay, now let me repeat that. The experiment is that you have a, a body, a heated body, and it gives out radiation. We call it black body radiation. The energy that we get from it has units of energy which are very discrete. So if I were to say what is discrete versus non-discrete or continuous, it would mean that you may get energy which is 1 joule, 10, 2 joule, 3 joule, 4 joule, and so on. That's the unit of energy that we know. But what he saw was that the energy was coming at very specific values, maybe 2.2 joule and then 3.8 joule. I'm just plugging in some numbers. But the experiments gave us this information that there are quantized states of energy that was coming out of that. Now, this is the origin of the word quantum. It's quantity, right? So when you say quantity or quanta, we talk about very discrete values of something, or quantized values or quantized levels. So that energy was described by a factor what they call h mu, which is shown in this figure. And this is the fundamental relation that we have seen before. We saw it as where we were talking about how do we convert wavelength into energy. Remember, there was this plot where we were talking about band gap. So the fundamental relation there was hc over lambda. This is no different. There's the same relationship because c over lambda is equal to frequency, which is shown as mu here, right? So E is equal to h mu. And we'll talk about what is q phi here, what is the minus quantity here. But so far with me, this is a very fundamental relationship, and it's called dispersion relationship. This is called dispersion relationship, and you have to you'll have to remember this. We will encounter this over and over. We will use this to explain whenever we are converting uh, wavelength into frequency. Dispersion relationship, which is mu equals c over lambda. Frequency is equal to c over lambda, where c is the speed of light and lambda is the wavelength. All right, so what he measured that the different values of the energy with respect to the voltage, and he saw a straight line. So this straight line, if you extend it all the way to the y-axis, you see that it hits y-axis some energy level, what we call as phi. Now, q phi is an energy, right? Q phi is a relationship for energy. Now, this energy is what you would require to keep on applying that uh, energy until we get uh, light out of that material. So there is a specific thing. Now, this is now known to be a very specific energy for every material, and we call it work function. So you have to apply that much energy before uh, a material will start giving out photons. Now, this relationship is very fundamental in a sense that we can now use this to figure out what kind of wavelength we are getting, because that will tell us what is the energy of the radiation that's coming out of a material. Now, if you look at the relationship of this energy with the wavelengths, we continue on to another experiment where there was this gentleman called Young. So he did a double slit diffraction experiment. And what did that experiment do is basically you have two very small apertures or in a screen, and when you shine light, and you have one source of light, but on the other side, two slits would show up as two sources of light. And their light, once it hits the screen, will show some places where it is bright and some places where it is dim. So, uh, which was basically a way of knowing that the light is traveling as waves. Now, at the place where those two waves are intersecting and they are supporting each other, we get constructive interference. They support each other, so you get a bright line there. And where they are out of phase, they result into destructive interference, which gives you a dim space. Now, so far it's okay, it's a wave. But when they dim the light, they wouldn't see those bright and dark regions, but they would see specks. They would see spots of light that reach on the other side. So which means that light is not traveling as a wave, but light is traveling as individual particle. So this is the idea, what we call as wave-particle duality. That the same light can result into diffraction pattern where they would interfere with each other. And the same light would give us a behavior where it would strike like a point on the screen. So please stop me if I'm going too fast, but these are just simple experiments which have led us to develop the theory, which we call as wave particle duality. Because now when we deal with electrons or when we deal with charge, we will be talking a lot of times, we will be treating them as waves. So we have to know that why we would be converting our discussion in waves while we think of a particle or an electron as a something that has a mass. We will talk about the mass of electron also. So this is where we have to establish this, that it has both properties, wave particle duality. Now, when you say wave particle duality, there is, if you talk about wave, it has lambda, it has wavelength. This is what is shown here now. A little bit derivation, but what it does is it connects the wave property lambda equals h over p into ultimately our p is momentum, which is mv, mass times velocity. Now, what we end up getting is we get momentum equals h over lambda. So momentum in terms of wavelength. Now, if you multiply and divide this expression on this side by 2 pi, h over 2 pi, h is Planck's constant. H over 2 pi is what we call as h bar. Planck's constant divided by 2 pi. And this side is what we call as K. Now, K space is something we have talked in micro lecture in last module, which is basically the frequency domain, frequency space. Now, if you think about it, we can use the dispersion relationship here as well, and we can uh, convert what we have done here. We have converted frequency into h over lambda here, right? So this establishes some basic ground rules for us that whenever we think of a wave, okay, this is the experiment that I was talking about, that two waves coming through very small slit. On the other side, what you see is at some places they are supporting each other, and at some places they are opposing each other. So there's constructive interference, there's destructive interference. And this gives us on the screen the true nature of a wave as it's traveling and it's interacting each other. So this is now shown that if they add to each other, the total becomes larger. If they are interfering destructively, what you get is they cancel each other out, right? So now, having established that, again, remember that whenever we'll talk about electrons, we'll be using it in a lot of times in frequency domain, but we will be treating it as a particle. And that comes from this understanding, what we call as wave particle duality. All right, questions? Are we, okay, I know these are all new ideas, or maybe you have seen those before, but we are going to apply these ideas on real situation, what we call as electron or charge movement in a device. All right, so now where do we see these? We see this when you see any neon sign, we see this happening. So what is the phenomena in neon signs? Can somebody tell me what happens in neon signs? It's the same black body radiation concept. What happens in a neon sign?
Is it the neon gas that reacts to the electricity?
Neon sign reacts to electricity. Very good. Who said that?
I did. Is that
Okay.
you?
You say I did. It's a big room. Alexis, is that you?
It was Sergio.
Oh, Sergio.
Yes.
All right. Yeah. So I'll just modify what you said. It's not reaction. So we fill a tube with neon gas and we give it energy. We supply it energy, and energy is electric current. So you give it current. What happens? You give it energy. What does it give out?
Light.
Photons. Let's light, exactly, photons. We'll talk about photons now. Now, different neon signs give different light. Sometimes we just coat a color on top of them. But different gases would give different wavelengths. Why is that?
Because the electrons are at different energy levels.
That's where you see quantum theory, quantization of energy. Each material would give very specific energy wavelengths, right? It would give very specific wavelength. I shouldn't say energy. Energies, we are pumping energy. It would give very specific wavelengths. Of course, wavelength is directly, it's inversely proportional to energy. So now, here's the thing. If you have a neon sign, it has neon gas, and it gives out specific wavelengths. If we keep on pumping more energy, would we give more wavelengths?
No.
It's Joel. You are right on the money. The rest of the class, do you understand what I just asked? If you say you are giving it, I don't know, 200 millivolts, then you say, okay, I'm going to give it 100 millivolts and increase my, sorry, energy should be in watts. So I give 100 watts and I'm going to say I'm going to give it 1000 watts. Is that going to change the wavelength that comes out of it? Is that going to
No.
start giving out? It's going to keep on giving out exactly the same wavelength that it gives. So if you think about it, that's the quantization of energy right there. It may increase the number of photons that come out, but it is still going to give out just that same wavelength. Right, Omar?
Yes, so I was going to say, like, the wavelength of light kind of corresponds to the color. So, like, pumping more electricity wouldn't change the color. It would just increase the brightness.
It just increased the brightness and gave us more. That was the fundamental experiment, what you called as photoelectric effect, what we started today, right? The photoelectric effect. Now, this is where, you can see right away that it doesn't follow our understanding of other things that we do. You pump more energy, you should get more things, but no, we get just quantization of energy. You may be giving more energy, but what you get out is very quantized. And that's what we say that it's it needs quantum mechanics. Now, here there is the third bullet point says something interesting. Intensity of the emitter noise is measured as a function of wavelength, nothing else. Now, if a material gives more than one wavelength, it's just going to give those wavelengths, and that's what would lead to a few more experiments that we're going to see. And that ultimately will lead to the concept of band gap, which we had just talked about band gap like something in a plot, but we haven't really thought about where it comes from. A series of sharp lines rather than a continuous distribution of wavelength. That's what we would get. We would get maybe one wavelength and then go on and then get another wavelength and keep on going through and getting different wavelengths. This is a real plot from measured by three scientists long time ago, Lyman, Balmer, and Pachin, I don't know how to say this. What you see here is very discrete lines on the wavelength spectrum. What does it mean? They were using material, pumping energy, and they would get just very specific wavelengths and not others. Hence the idea of quantization. Now this is what we call as atomic spectra. When you say spectra, spectra is this distribution over a broad range of whatever thing we are measuring. What is this relationship on the right hand side? Lambda equals C over frequency, C over mu. What do you call this relationship? Dispersion.
Wavelength.
Dispersion relationship. You have to just remember it by heart. This thing is called, this will come over and over, dispersion relation. So simple way to go from wavelengths to frequency, right? Simple way of going from wavelength to frequency or frequency to wavelength.
I'm sorry, are you saying dispersal relationship or destructive relationship?
No, dispersion. Right? So, and with this, we connect energy with wavelengths, right? So now here in this relationship, H is constant, C is constant, right? We might as well just find what is the relation, what does this HC mean? How much is HC? 1.24. Just remember that. Wherever you see HC or E relationship, it's going to be 1.24 electron volt.
So is that a constant then?
It's a constant. H is Planck's constant, C is speed of light. For us immortals who travel at low velocities, C is constant for us. You know what I'm saying. If I move too fast, theory of relativity says that light will slow down. But we will always, whenever you see energy or lambda, you will always say, okay, E equals 1.24 divided by wavelength. I don't know how to write lambda and zoom. Right? That is straightforward relationship. Now you can understand that plot we saw where we had energy, band gap energy on one side and wavelengths on the other side. Now, this means that, okay, when I'm showing you that there is only very discrete lines of wavelength then coming out, that also tells you that there are very discrete energies that are coming out. So whatever wattage you pump in your neon sign, there are many more things we use. For example, all the optical devices we use, they are defined to give out specific wavelengths. That's the solid state devices, optical solid state devices. All right, you guys have noted down these things. Let me just clear those. Now, they were doing these experiments and they were finding these characteristic emission spectra. This is now spectra of the sun's prominent lines, absorption line spectrum from the sunlight. Sodium, hydrogen, calcium, what is Hg? Mercury and neon. They all have very specific spectrum from a light bulb. Now, you see the top two are showing much more. They're showing a spectrum instead of discrete lines. What is that? That's number one. That's the continuous spectrum from an incandescent light bulb. That's your light bulb, right? That's why the light shows as white. You with me on this? What am I showing here? Okay, these numbers are not very clearly written. Let me just type them. So this is number one. This is number two. And then there keeps on. You see this, it's not clear. This is sodium, this is hydrogen, this is calcium, this is mercury, this is the. So when you have mercury light bulbs, they are made of mercury, but they have other materials to cover all the other spectrum, so you get white light. Right? You guys know your white light is, there's no frequency, there's no wavelength for white light. White light doesn't exist, you know that, right?
Yes.
White light is the mixture of all these wavelengths, which is shown here in number one. That's your light bulb. Right? Number two is your absorption line spectrum of sun's prominent lines. All right, so now when you see this, how are they related to each other? It's something interesting that there is a certain order to how they, now for each one there is a certain energy level, right? Those energy levels are related. We found out those energy levels are related to each other. If you, now you saw Lyman, Balmer and Paschen wavelengths, right? If not, take a screenshot because we're gonna be talking about this. It looks kind of random here, right? But it is not random. When they pick up these wavelengths, these energies, they found there is certain relation between them. That E21 and E32, if you add those up, you get E31. I'll let you absorb this picture before I start playing with your brain. What do you see here? All right. Can somebody tell me one thing you see here in this picture? Tell me one thing you see here. Doesn't have to be hyphen, just any simple thing you observe here in this picture.
The subscript increases as the energy rises.
So if you add two of those, you can get third one, right? So like this one and this one, if you add those, what do you get? You get this one, right? So they're coming from different times, different people, but you see some kind of relationship with them. If I were to look for this guy, I can easily see that this is made up of two fundamental ones. It's just 5 levels shown, but you can see, for example, if I take this guy and I subtract this guy, what do I get? I get this guy. Are you following? Let me just clean this and start again. I'm making too much mess. So if I would take these two and subtract smaller one from the larger one, what do I get? If I take these E32, right? So this is a common thing among all of them. So what we are seeing is some kind of relationship between those two. And these are just from hydrogen. These are spectra coming from one atom, hydrogen. So if you were to write it down, what we see is there are relationship amongst photon energies. And these equations explain those relationships very clearly. Now, there are a few things here. One is R is a constant. It's called Rydberg constant, right? It is some number divided by distance. Okay, what else is here? Speed of light, okay. What else is here? N. N is a number where it is a, what do you call it? A whole number, 2, 3, 4, 3, 4, 5, 4, 5, 6. For 3 relationships, it has a unique value to it. What does that number tell us? If you were to put this in perspective of dividing and subtracting, this gives us a relationship between any two energy, or what you call the photons that are coming out of that relationship, just by plugging in that number. But you have to just remember this, and we'll come to N later on. This bold N is just something which shows us there's a relationship between those two. All right, questions?